Hello, good morning, beans. It's time to rise and shine. And man, I really like music conditionally. How do I turn this beautiful art into an automatically generated audiovisual experience? If you said artificial intelligence, you still have time to rethink your sentence. The answer is a music visualizer, specifically the texture that generates the data. Actually, we already have audio. I'm here to teach you how to make your own music visualizer texture. Why? Let's do a theory first. Thanks for assisting my class. Now let's do the practice. First, set up the visualizer assets. Where will we process our audio? A script. That could work, but keep in mind that we can make use of something faster than this. That's right, a shader. Oh, that would be awesome. Unfortunately, VRChat doesn't support compute shaders, and it probably never will. So we have to use a custom rendered texture. For starters, a custom rendered texture or CRT is used to compute images using a material. It can be to calculate heavy things at a lower resolution, process data in a chain, random. In our case, we will use it to convert an audio input into useful data. To input the data, we do need a script, whose function is to get samples from the audio stream that a source is playing, then send it to the shader that will process this data to the CRT. So to start, we need 4 assets. The script that sends the audio data, make sure it's an Udon Sharp script, the shader that processes it, plus a material for it, and the custom rendered texture that the shader will write to. Now we have to mash these assets together. For the material, we already know that the shader will be the one that we created. The CRT will need some tweaking before use. First, the resolution. This is arbitrary. It will change depending on how much data you want to get from the audio. In my case, it will have a width of 512 pixels to ensure I can render a spectrogram with enough detail. And the height will be 8 pixels, just in case I want to add more data. The format will be a 32-bit float with 4 channels, so we can store any value no matter the dimension or the precision. The texture is meant to contain non-visual data, so we don't need to interpolate between pixels. And it will update constantly while the audio is playing, so we will set the update mode to real time. You can also see a material slot in the CRT, that is where we will put the material we created. Now everything is set up, now we can start writing, starting with the script. First, the input variables. A public audio source component for the source that we will read from. Then a public material for the material we will send the data to. Then a float array that will transfer the data from the source to the material. On the start, we initialize the float array with the amount of samples we will take from the source. Keep in mind that you cannot send float arrays greater than 1023 to a material. Then on the update function, we'll read the output data from the source, with the destination being that float array. Then using the material setFloatArray function, we will send the data to each shader. You can use any name for the shader property, but make sure to remember it. The script is ready to be used now. You only need to create an audio source for your scene, then add the script to any game object. It can be the audio source itself if you want, then set its respective parameters. Let's do the shader now. First of all, this shader is meant to run on a custom rendered texture, which has its own vertex program and data. To apply it, declare the vertex shader as custom rendered texture vertex shader and rename B2F on the fragment shader as B2F custom rendered texture.
Hi, hello. It's editing stereo here. I forgot to tell you to include the file called Unity Custom Render Texture.cg and to remove the structures and the vertex shader and the fog declaration because you're not going to use any of them. Like why do you want to keep it? So yeah, my bad. Yeah, let's continue.
The last step to set up our shader is to declare the float array that contains all the audio samples. Since it's an array and it's pretty large, we will read it from something called custom buffer or cbuffer. Don't ask me what this thing does, aside from assigning a block of memory for the GPU. I search everywhere and no one wants to explain it. Fragment shader. Clear everything, I don't want to see these lines, they scare me. Get the coordinates of every pixel as a 2-axis integer, using the input variable named global text chord. Be aware that there's another variable named local text chord, the difference being that it has the texture coordinates of the zone that's being rendered, instead of the whole texture. It will make sense later. To get the identifier of every pixel, you have to multiply these coordinates by the resolution of the texture. The resolution of the texture can be accessed from a variable inside Unity custom rendered texture.cging named _custom rendered texture info. The x and y axis are the width and height respectively, and the z axis is something for another day. I swear to God, it's getting too hot in here. I shouldn't have put out my headset at daytime. So multiply the global coordinates by the x and y axis of the custom rendered texture's resolution. Next up, test that everything looks correctly by returning the sound array with the index being the x-axis of the coordinates we calculated. If you did everything correctly, your output should look like this. Now with everything set up, we can start by getting the frequency domain. Quiz time! How do you think most waveforms get converted from a spectrogram? A. Using an advanced yet lightweight algorithm. B. By reading every sample for every frequency and hope that it matches. C. Executing a built-in DirectX function named getDFT. D. No, as a general rule. If you guessed A, let me tell you, I wish this was true. But unfortunately, the answer is B. The algorithm is called discrete Fourier transform, and in reality it's not as complex as you might think. This algorithm works by multiplying the audio waveform with another waveform at a certain frequency. If you sum all the samples on the result together and divide it by the number of samples, you will get the intensity of this frequency. This function would take n raised to the power of 2 iterations to compute, with n being the number of samples we received, because every frequency would have to read through every sample individually. But lucky for us, we're doing that on the GPU, which is made to compute values in more than 0 dimensions. So the cost is reduced from n raised to the power of 2 to just n. Kinda. Let me explain how this works. You might know the sine cycle looks like this. It has a positive peak and a negative one. They have the same magnitude, so if you add both together, the result will be 0. If you multiply a waveform with another one that has nearly the same frequency, the negative values will get negated, making it positive, or vice versa, making the positive values negative. So the closer the frequencies on the waveform are, the larger this value will be. We could make use of something called the fast Fourier transform, but just as with every formula I want to learn, nobody wants to give an understandable explanation on how this works. If I get to understand it, I will make a video for it. But there's an issue. If the input waveform and comparison waveform are shifted by a quarter of a cycle, half of the result will be positive and the other half negative, making the sum 0. The solution is simple. We can make use of the cosine, which is the same function that the sine, but shifted by a quarter of a cycle. Now the magnitude of the sine and cosine sums will give a stable value. The next step is getting a frequency for each pixel. We already have the gradient as the global texture coordinates vector's x-axis. First, we have to convert this 0 to 1 gradient to a 1 that goes from the lowest frequency we want to read to the highest. That is up to you to decide. In my case, I chose 50 Hz as the lowest and 20,000 Hz as the highest, which is the point where most humans cannot hear higher frequencies. Some people can hear up to 28,000 Hz, and that's why most sample rates for audio are either 44,000 or 48,000, where the highest frequency will take only 2 samples to complete the cycle, which will be 22,000 or 24,000 Hz. That might sound like a bunch of unnecessary information. To convert the gradient, first we have to multiply it by the highest frequency minus the lowest frequency. Add the lowest frequency to the result, then floor it. Obviously, we are not done yet. The amount of samples we are taking every frame does not equal an entire second. The time in seconds that this waveform represents will be the audio's input sample count divided by the audio source sample rate, which in most cases is 48,000. Although you don't really have to be that specific for this case. I know what you want to do is see the funny blobs move up and down. The last step is multiplying it by 2pi, which you can get from the file unitycg.cging as unity_2pi, or write it by hand as 6.2832. No, I will not add more precision to the number. Also, thanks Pi for letting me keep the shaded clock. This was the best ViaChat update ever. Now we will create the variable for the result. The result will contain both the sine and cosine comparisons as a float too. Then we will create a float variable that represents the path of the sine and cosine cycled for every sample, starting at 0. I will call it phase. Following that, we will have another float variable for the delta or difference between every sample, which will increase the phase until it equals the frequency ramp. In my case, my audio input has 1023 samples, so this variable will be the frequency ramp divided by 1023. Water. Tasty. Now create a for loop that iterates by as many samples as the audio input provides. Every iteration, add to the result the audio input array, with the iteration being the index. Multiply by a float to where the x-axis is the sine of the phase and the y-axis is the cosine of the phase, and following that, sum the phase by the delta. After the for loop, divide the result by the number of iterations, and then get the length of the result to convert it from two values to a single average result. This is your DFT or frequency domain. But wait, why do the frequencies that I want to focus on are so tiny? That's because frequencies don't increase at a constant rate. Take octaves as an example. C1 is at 55 Hz, and C2 is double of that. C3 is the double of C2, and so on. Take for example this DFT analyzing the frequencies of the same note at different octaves. Instead of having a constant difference between frequencies, each note gets further away from each other the higher the octave is. And I was going to tell you to use a random formula I made to get a better distribution of the frequencies. After all, nobody wants to let you know the formula you're looking for even though they have the whole articles where they talk about it. Nobody, except That's right, I found the equation that works better than mine. In Shaded Toy, the original source comes from Stack Overflow, which the shaded author credits above. So I want to give a massive thanks to Ed Tide and Gerard Abello for providing this equation and making me realize I'm stupid. Because after seeing this simple formula, I remembered that a logarithm is just an operation to know at what power has a number been raised to. So to get the inverse of a logarithm, I only need to raise x number to the power of the logarithm's result. So we have to turn this linear ramp into a variable gradient that adjusts the frequency distribution so the difference between lower and higher frequencies is closer. Do this by replacing the frequency's gradient's first step by an arbitrary number higher than 1, raising it to the power of the gradient we replaced, subtracting it by 1, and finally dividing it by that arbitrary number minus 1. The higher this arbitrary number is, the wider the lower frequencies are. Now look at the result. Isn't it kind of chaotic? That is not unexpected. It happens because the intensity of the frequencies is not constant on the input waveform. And to solve that, we need to make use of something very helpful on a custom rendered texture, the double buffer. A CRT gets cleared every frame, then rewritten, but if the double buffer box is checked, the CRT will keep a copy of itself before being cleared. That's called back buffer. But there's a problem. We want to read the buffer as a list of exact data. And Unity custom render texture.cging only gives us the back buffer as a sample 2D called self-texture2D. The issue with sampler 2D is that you can only take data using normalized texture coordinates instead of integers as the pixel's location on the buffer. And I'm not a big fan of using float numbers for that. Using the define command, replace self-texture2D by a random name before we include Unity custom render texture.cging. This will replace all mentions of the back buffer texture by a non-existent texture, in this case only the sampler 2D decoration, and then undefined underscore self-texture2D, so it doesn't replace the name after this line. Now you can declare underscore self-texture2D as a texture 2D instead of a sampler 2D. The value we want to get from the previous frame is the DFT. We know it's expanded across the entire texture's x-axis and it's expected to be located in the first pixel row. So the index of the texture will be an integer 2, with the x-axis being the x of the pixel index we calculated a while ago and the y-axis being 0. Now create the float variable which will blend between the previous DFT and the current one using the lerp function. The lower the factor is, the slower the DFT will change and vice versa. You can adjust this to your liking by having the blend factor as a range property that goes from 0 to 1. I also want to add something else. It's a simple yet effective line that will help you reduce the wobbliness of the DFT. When you set a low blend factor, the less chaotic the DFT is, but that doesn't look so good with faster music. If you set the factor higher, it will react faster, but there will be too much chaos. While doing some tests, I found something that can help reduce the tiny oscillations while keeping the big ones. That formula is the absolute of the previous DFT minus the current DFT. As you might tell, this is just the intensity difference that the DFT is expected to move forward for the next frame, which is... yeah, it's expected. This line is a lerp between the previous DFT and the one we just calculated. Make the blend factor adjustable too by multiplying the DFT difference by another range property. We have a cleaner DFT now. To store it into the texture, we can take advantage of the RGBA pixels to draw it on the same row, but this time on a different color channel. To do that, we create a float for color for the DFT result. The red channel will be the unmodified DFT, the green channel will be the smooth DFT, and the blue channel will be used for the next step on our DFT. I am talking too much and I fear I will spend another 3 months editing this video. The last step I want to do is remove a bit more noise by expanding all frequencies into blobs that take over the tiny ones. I proudly named this method DFT bore, and I will not accept any request to change that name. The way this works is by iterating from -n to n, with n being the range that the frequencies will cover. The value is arbitrary and so it can be an integer property. The frequency will expand in the form of a Gaussian gradient, which can be calculated with the following formula. This way, the intensity of the frequency smoothly fades out the further away it is from the actual position. To start, create a float variable for the final DFT, starting at 0. Next, create a for loop that will iterate from minus the number of iterations you created as a property to the positive of that same number. Make sure that the comparison is lower or equal, so it iterates as many times on the negative side as the positive side. Charger, where's my charger? It's charging! Inside the loop, create a float for the face, which is the iterated variable as a float divided by the property that represents the number of iterations, also as a float. Then create another float for the DFT we're going to compare, which is underscore self-texture2D screen channel, with the x coordinates being the horizontal pixel number plus the iteration variable, and y being 0. Multiply this by the exponent of minus the face multiplied by itself, which is the Gaussian gradient. The final DFT will be the maximum between itself and the DFT we sampled above. This will go to the blur channel of the result, and on the alpha channel simply put the waveform we sampled on the first stage of the shader.
Yeah, technically I didn't mess up this time. I want to give you a small tip. You might have noticed how the higher frequencies have a lower intensity, and yeah, that's not like a fault on the DFT or something, because I did test it with various audio samples, and yeah, it's just how audio mixing works. I wish I could give you an exact formula to compensate the intensity on all frequencies, but I guess I don't need to tell you why I cannot give you an exact formula. The solution I usually rely on is getting the XUV gradient, multiplying it by a big number, just whatever number you feel like it's working okay, and adding it by 1. And yeah, you multiply the DFT by this, and you should have like more visibility for the higher frequencies. Yeah. Goodbye.
This is how all the DFTs you calculated look, including the waveform. Customize this to your liking with the properties you created. Now all we need to do is make this section render where it's supposed to be rendered, on the first row of pixels. Add a new update zone to the CRT, set its update zone space to pixel, and adjust it correspondingly. The X center is the center of the texture, so half the X resolution, and the width is the whole texture, so the X resolution. This is done already, so you don't need to modify it. Next, the Y center is the center of the first pixel, so 0.5, and the height is 1 pixel, so 1. You can see that the pass appears as unnamed. To give it a name, you only need to go below the line where the pass starts. Then write name in capitals, followed by the string containing whatever name you want to set. Now that you have the DFT and waveform, you can do anything you want with that. Let me show you an example. We're going to get the main intensities of different sections from the DFT. It can be 3 or 4 or any amount. In my case, it's going to be 3. Low, middle, and treble. To start, duplicate the previous pass. Delete the fragment shader. These lines still scare me. And set the name to something different. Call it 3 band or 4 band or whatever number of bands you want to read. Then add a new update zone with its pass. Put it somewhere that it doesn't overlap with another pass. I will move it to the second pixel row at Y 1.5 with a height of 1 pixel. And starting from the left, it will cover as many pixels horizontally as bands you want to get. In my case it's 3, so its X location will be 1.5 and its width will be 3 pixels. Now go back to the fragment shader. First, get the pixel identifier as an integer 2 again. That is the global texture coordinates multiplied by the texture resolution. Now get the X coordinates to indicate the identifier of each section. If your block is offset from the side, you will have to subtract it by its X pixel position. So the first identifier of the block is 0. What we will do now is read through the DFT, divided by as many sections as bands you want to read. So every pixel will offset the coordinates we will read from by a block. And then we will read through all samples inside that block. It's as simple as that. Make an integer to represent the size of each block. That is the number of values in the DFT divided by the number of bands. Don't worry if the division returns decimals. Remember that we are here for the funny blobs, not accuracy. Then create another integer for the DFT offset we will read from, which is the block size multiplied by the identifier. Now before iterating, think what you want to get from this. Why are you doing this? What's your purpose? Please let me go, I have 3 cats to feed. I will get the average, maximum and minimum value of each band. To calculate every value you'll need a different operation, so it will be better to have these values as 3 different floats. The maximum and average will start as 0, and the minimum as an arbitrary value that's higher than what the DFT is expected to reach. I will put it as 10. Don't ask. The cat killed curiosity. Start a for loop that will iterate for the block size. Every iteration we will sample the DFT on a float from underscore self-texture 2D, with the coordinates being the block offset and 0, and the channel being blue or Z, where the final DFT is. For the average, add the value to it. The maximum will be the maximum between itself and the value, and the minimum will be the minimum between itself and the value. Lastly, increase the block offset by 1, so the next iteration it will read from the next sample. Fuck. After finishing the loop, divide the average by the block size as a float. and return these values as a float 4, with the alpha channel being 0, because I don't plan to put anything in there. And that's how you can make a music visualizer texture for ViaChat. This last step is optional, and it's globalizing the texture. By that, I mean making it accessible to everyone, which can be any material in your world or any player's avatar. For that, go to the script that sends the data to the material, add a public custom render texture property, and in the start function use the shader setGlobalTexture function. The first input will be the shader's getPropertyID function, with its value being the name you want to use for the texture. Make sure it starts with _udon and it doesn't match any already existing names. The second input will just be that custom render texture property. On the inspector, set that property as the texture where we calculated everything, and that should be it. Just declare a texture 2D object with that exact name, and make sure you don't have any property with that name, otherwise it will be overridden. The bands were just an example to show how you can do whatever with the data you generated. I will obviously make another video where I show examples and more functions you can do with this. That hopefully doesn't become as long as this video. I cannot really tell you when will it be, because I'm working on different videos and worlds and avatars, and I still have to update that avatar base I made on Gumroad. But anyways, thank you so much for letting me hold you hostage, and now go do cool stuff with your music visualizer.